Hello everyone, welcome back. In this particular video, we're going to talk about electrophilic aromatic substitution reaction in more detail. Specifically, we're talking about electrophilic aromatic substitution on compounds that contain a substituent. And the topic that we're talking about is activating and deactivating groups. So activating groups and deactivating groups. As I mentioned, this applies to compounds, aromatic compounds that contain a substituent. Now, I'm using benzene-containing compounds as an example here, but whatever we learn here can be applied to other classes of aromatic compounds. It is not limited to benzene-containing aromatic compounds. So the substituent on an aromatic compound, it can make the aromatic compound electron rich or electron poor. Now, when the aromatic ring becomes electron rich, then it's going to be more reactive in the electrophilic aromatic substitution reaction. And in this particular case, the substituent is referred to as an activating group. On the other hand, if the substituent makes the ring, the benzene ring, electron poor, then the ring is going to be less reactive in an electrophilic aromatic substitution reaction. And in this particular case, the substituent is referred to as the deactivating group. So important thing to keep in mind is that when we say a group is activating or deactivating, we are referring to the substituent on that aromatic compound. That substituent is what makes the compound or the aromatic ring activating or deactivating. And activating and deactivating, they refer to whether the compound is more reactive, which means would it undergo the reaction faster, or less reactive, which means it would undergo the reaction slower. So that's what we need to keep in mind here. Activation means a compound that's reacting faster, and deactivation means a compound that's reacting slower. Now, in case you're wondering, faster and slower with respect to what? Our reference here is benzene. So when we say more reactive or less reactive, we're always referring to benzene, because these are all benzene-containing compounds that we are discussing here. So as a few examples, I've chosen various substituents on a benzene ring. The first one is toluene. Now, toluene, if you look at it, it has a methyl group as a substituent on the benzene ring. Now we can generalize the methyl group as an alkyl group. So toluene is a representative of any alkyl group on a benzene ring. Now in this particular case, what we know is that alkyl groups are electron donating. These are electron donating by induction or through hyperconjugation. So there are two effects that we can talk about here. We can talk about induction, or we can talk about hyperconjugation. So the alkyl groups are electron donating to the ring. And so essentially what that means is the presence of an alkyl group is going to make the ring electron rich. So the ring has a higher electron density, again, reference to benzene here. And so because of that, because it's electron rich, the ring here would undergo electrophilic aromatic substitution much faster, much more easily, because it's more electron rich. And in terms of mechanism, recognize that what happens is that the aromatic ring behaves as a nucleophile. So it goes and attacks the electrophile. So if it is more electron rich, it would be able to do that attack much more easily. So what happens here is that because the ring is electron rich, it will be more reactive. And hence an alkyl group is an example of an activating group. This is an example of an activating group as far as electrophilic aromatic substitution is concerned. The next example we have is anisole, which is methoxybenzene. So we have an ether connected to, or a methoxy group connected to the benzene ring. Now, as you can imagine, the oxygen is electronegative, more electronegative than carbon. So as far as methoxybenzene or this methoxy group is concerned, it's going to withdraw electron density from the ring inductively. Again, inductively, the methoxy group would be electron withdrawing. Okay, so it is inductively electron withdrawing because oxygen is more electronegative than the carbons. But that's not the only effect here. There is a resonance effect that we can see. Okay, there is a resonance effect that can be seen. So essentially what that means is we can draw some resonance forms for methoxybenzene that involve this lone pair on the oxygen atom. Let's draw some of them out. So if we start with methoxybenzene, you have OCH3, lone pair on the oxygen and the aromatic ring. So I can start with the lone pair on that oxygen, push it down. Simultaneously, this double bond would come here. So the next resonance form is going to be OCH3. But now we have a double bond over here, lone pair, positive charge on that oxygen. There is a negative charge here, double bond and double bond. Now we can use this lone pair to do further resonance. And so we can draw the next resonance form. We have double bond OCH3, lone pair, positive charge over there, nothing changes over there. But the double bond is now here. There's a double bond over there and lone pair there. So we have 3 resonance forms, but we're not done because we can take this lone pair, push it up. The electron pair goes over there. So we can draw further resonance forms here. Double bond OCH3, positive charge. A double bond here, and a lone pair over there. And then finally, we can draw another resonance form where we bring this back and the lone pair goes to the oxygen. So the last resonance form that we can draw will get the methoxy group back. The lone pair comes back on the oxygen, a double bond here, and double bond here. So these are all the resonance forms that are possible for methoxybenzene. And if we carefully examine these resonance forms, what we notice is that the methoxy group, the oxygen lone pair, can be delocalized into the aromatic ring. And there are several resonance forms here, 1, 2, and 3, where there is a negative charge on the ring. So that means the electron density is enhanced on the ring. There is more electron density going into the ring because of this resonance. And so resonance effect enhances electron density, makes the aromatic ring electron rich. So we have an inductive effect, which is withdrawing electron density because oxygen is more electronegative. And we have a resonance effect, which works in the opposite direction by supplying electron density. And in the case of the methoxy group, what happens is resonance wins. Okay, so resonance wins, and therefore the ring is overall electron rich. So the ring becomes overall electron rich, which means the methoxy group can be treated as another activating group here. So the alkyl group was activating, and so is the methoxy group. That is also an activating group, because between the two factors that are competing here in opposite directions, the resonance takes over. And so that makes the ring overall electron rich. The next example we have is of chlorobenzene, and the chloro group here is representative of any halogen substituent on the ring. And we can draw some comparisons between the methoxy substituent and the halogen here. Very similar to the oxygen here, the chlorine is more electronegative than carbon atoms. And so essentially, inductively, the chlorine or any other halogen should be electron withdrawing. So this is inductively electron withdrawing. But because the halogen, the chlorine here, or for that matter, any other halogen would have lone pairs on it, or has lone pairs on it, there will be a resonance effect that we can talk about. There is a resonance effect that we can talk about. And we can write some resonance forms very similar to the methoxy benzene. So I would encourage you to actually work through those resonance forms. They're going to look exactly similar to what we have for methoxy benzene, except that the methoxy group is replaced by the chlorine. I'm going to get you started here. So the first resonance form that we have will have a chlorine with 3 lone pairs on it. Then we can use one of these lone pairs and we can start doing some resonance. So the second resonance form that we can write would have a double bond to the chlorine, 2 lone pairs, and a positive charge. And there should be a negative charge on this carbon, double bond here and double bond there. And then we can use this lone pair and do further resonance. So this is how we will get the other resonance forms. I'm not finishing it off, but we are able to write additional resonance forms. And what we're going to notice here is that, very similar to the case of the methoxy substituent, the chlorine lone pairs add electron density into the ring, where we have negative charges on the ring. But in case of halogen substituents, inductive effects dominate. Okay, the inductive effects dominate. And so overall, the halogens are a deactivating group. They are a deactivating group. So that means they make the ring electron poor, and so the ring is less reactive. So it undergoes the reaction slower compared to benzene. So the halogen is an example of a deactivating group, and we have a situation similar to the methoxy, where the inductive and the resonance effects are competing. Inductive effects withdrawing electron density, resonance effects adding electron density. But the inductive effects win here. The last example I have here is of nitrobenzene. So this is the nitro group. And so nitrobenzene is another example of a strongly deactivating group. It's a deactivating group. And that's because when we look at the Lewis structure for a nitrobenzene, this is the Lewis structure for nitrobenzene. And what you notice is there's a positive charge on that nitrogen. So that nitrogen with two oxygens connected to it with a formal positive charge on it is a strongly electron withdrawing group. So this is electron withdrawing. This is a strongly electron withdrawing group, and we get the nitro group here. And additionally, because of this Lewis structure for nitro, we can actually draw some resonance forms here as well. So I can start with this Lewis structure and start drawing some resonance forms. And because the nitrogen has a positive charge on it, it's going to withdraw electron density. So I can push this lone pair up, and simultaneously I will have to push that pi bond away. And so we will get the first resonance form where we will have double bond N, O minus, and O minus with a positive charge, like that. That's going to be one of the resonance forms. I haven't finished it. Double bond here, and we will get a positive, a formal charge on the ring carbon. And now we can do further resonance. So our next resonance form is going to be double bond here, double bond here, double bond to the nitrogen, oxygen, oxygen, negative charge, and positive charge here. Positive charge still on the nitrogen. And further resonance is possible. Double bond nitrogen, O minus, positive charge here, double bond, and positive charge over there. And then one final resonance form where we can bring this lone pair back, push this pi bond away. So we'll get N double bond O minus, positive charge still there, double bond here, and double bond. So those would be all the resonance forms of the nitrobenzene. And what we notice in these resonance forms is that unlike the case of a methoxy substituent or the halogen substituent, which were adding electron density to the benzene ring, and we could see that using the negative charges that were being generated. Unlike that situation, in the resonance forms for nitrobenzene, we actually are putting some positive charges. So there's a formal positive charge that is developing on the benzene ring, which basically signifies that the ring is electron poor. So the ring is electron poor, which means this is a deactivating group. So going back to the mechanism of these reactions, the electrophilic aromatic substitutions, the benzene ring or the aromatic ring acts as a nucleophile. So the amount of electron density in that aromatic ring is a very crucial factor. And what we see here is we have some groups like alkyl groups and methoxy groups that add to the electron density of the aromatic ring, and hence they activate the ring towards an electrophilic aromatic substitution. The ring reacts much faster compared to benzene, which does not have any substituents. On the other hand, we have substituents like halogens, for example, chlorine or nitro, which decrease the electron density on that aromatic ring. And hence, the ring is going to react slower in an electrophilic aromatic substitution reaction. And these groups are called deactivating groups. Let's look at some classifications of these activating and deactivating groups. First, we are going to look at activating groups. So these groups all make the compound more reactive in the electrophilic aromatic substitution. And each kind of group demonstrates some characteristic feature. So strongly activating groups, these are characterized by the presence of a lone pair at the benzylic position. Now, if you're not sure about what the benzylic position is, this is the position immediately adjacent to the ring. And this lone pair can be delocalized into the ring. So for example, a phenol, which has a hydroxyl group on the benzene ring. So this oxygen, which is part of the hydroxyl group, that's sort of benzylic because it's directly connected to a carbon from the benzene ring. And this lone pair can be delocalized into the ring through resonance. So we can draw a resonance form for the phenol. So we will get one lone pair on the oxygen, double bond here, and lone pair there. So we can start doing some resonance over there. So that lone pair can be delocalized into the ring. Other molecules which fall into this category of strongly activating groups are a phenolate, so an oxygen with a negative charge. One of these lone pairs can also be delocalized. And aniline derivatives. So the parent molecule, aniline, which has a nitrogen with the lone pair at the same position, or any substituents on the nitrogen atom, those would also work. So that's parent aniline, that's sort of like a secondary amine equivalent of an aniline, and this is a tertiary amine equivalent of an aniline. All of these are strongly activating groups. The second category is moderate activators. These are characterized by the presence of a lone pair, again at the benzylic position, but this lone pair can also be delocalized outside the ring. And in that case, the group is moderately activating. Example being an ester, which is derived from a phenol. So you notice that there's a lone pair on that oxygen, which is right next to the benzene ring. But this lone pair can do resonance outside the ring with this acyl group. So there is another resonance possible that's outside the ring. And so it becomes a moderately activating group. And similarly, the amide, which is derived from an aniline, okay? And again here, I'll show this. So you can take this lone pair and you can do resonance on that amide. So it's a resonance, it's an amide that is derived from aniline, and that's also moderately activating. So the key is these groups, they are able to engage in resonance outside of the ring. They are moderately activating. So that's the resonance form for this amide. And here with the ester, we can do similar resonance forms. Then we have weak activators. Weak activators are compounds containing alkyl groups. So any R group on a benzene ring would be treated as a weak activator. So toluene, which has a methyl group, ethylbenzene, tert-butylbenzene, these are all alkyl groups and they're all weak activators as far as the electrophilic aromatic substitution is concerned. Okay, so those are the three categories of activators. Next, we're going to look at the various categories of deactivating groups. Strong deactivators exhibit a strongly electron withdrawing group on the benzene ring. Examples being a nitro group, an ammonium group where the nitrogen has a formal positive charge, or maybe a trihaloalkyl group where there are three halogens on the carbon, which is benzylic to the ring. Moderate deactivators, on the other hand, these are characterized by the presence of a pi bond to an electronegative atom, which is conjugated with the ring. It is a mouthful, but essentially what you're looking for is carbonyl or acyl derivatives. So when you have an aldehyde, what you notice is at the benzylic position, we have a pi bond to an oxygen atom. So we have a pi bond to an electronegative atom, and this pi bond is conjugated with the ring. What does we mean by that? I can take this pi bond and push the electrons over, and simultaneously I can take this pi bond, move it over. So we are able to do resonance with the aromatic ring, so that the resonance form that we get to is going to have a hydrogen here, oxygen with a negative charge, positive charge here, double bond and double bond. That would be a resonance form. So since we're able to do resonance here, that means this pi bond in the substituent is conjugated with the ring. Other examples of such functional groups are ketones, esters. Now, we've seen esters before as moderately activating groups. The difference between this ester and that ester is that in this ester, the carboxylic acid is based on the benzene ring or the aromatic compound. So the C double bond O, the acyl carbon is what's bonded to the benzene ring. Similarly, amides, nitriles, so all carboxylic acid derivative groups, those are moderately deactivating. Weak deactivators include halogens, so haloaromatics, when you have a chlorine, bromine, iodine at these positions. These are weakly deactivating. As we've seen before, there is a competition between inductive effects and resonance for these molecules. And what happens is inductive effects dominate. So overall, the halogen substituent is electron withdrawing as far as the ring is concerned, even though it is able to do some resonance. So those are the various deactivating groups. So I hope you find this discussion useful on how activating and deactivating groups are classified and what makes certain groups strongly deactivating or activating versus weakly deactivating or activating.